তো অ্যাকচুয়ালি বৃষ্টির জন্য খুব নেটওয়ার্ক প্রবলেম।
হ্যাঁ হ্যাঁ, তাই হচ্ছে, অনেকক্ষণ ধরেই হচ্ছে এটা। Now it is visible, I think.
Now it's audible, sir. It's we can see.
Is this visible?
Yes, sir, it's visible, and
Yes, it's
we can.
visible.
Piezoelectricity. It is given as piezoelectricity. Okay. So what I have told you. So actually, so that means a mechanical energy or mechanical force will generate, so that property can be used for designing different types of micro actuator. So that means the piezoelectric material can be used either used as either micro sensor, then it is a direct piezoelectric effect, or it can be used as an actuator when you are talking talking about some micro actuator purpose. You are taking help of converts piezoelectric effect. Okay, so different micro actuators can be used, can be made using this concept. Okay, so a material whose crystal structure actually the material whose crystal structure that will lack a center of symmetry can show only the piezoresistive effect. The now the effect which is characterized by the charge sensitivity coefficient, and which is known as here Dij, that is coulomb per Newton. Okay, C/N, so coulomb per Newton. Now it relates the amount of charge which is generated at the surface of the material, okay, which has got area, suppose A, on the I-axis to the applied force F on the Z-axis. Okay, so it is I, J, these are the axes when you about to consider certain crystal. Like I have said earlier in some slide previous classes. So there is a crystal, and there the crystal is always recommended in certain axis. Okay, a certain pattern. It is cuts into certain axis wise. So IJ, these are the axes. Okay, IJ, these are the different axes. Now, if we apply force on the J-axis, then the I-axis, you will get some charge which is generated, and that is basically Dij, which is will get. So D here, which is equal to epsilon R into E, and it's a well-known relation. So E is the electric field. Here it's a displacement. Epsilon R is the basically the permittivity, so that is equal to epsilon not E plus P, and this delta Qi,
Hello.
which is the charge generation due to the applied mechanical force, which is given by small Dij del Fj, which is again written as Dij delta delta sigma into A. Okay, so that here the equation, it is the charge generation equation, and with that form, this charge accumulation, you can extract some voltage at the two surfaces of that material. Here now the material that is called as ferroelectric material. The ferroelectric material will have piezoelectric effect. but all piezoelectric material are not ferroelectric material. So converse is not true, but all ferroelectrics are obviously piezoelectric. Okay.
All
So,
ferroelectrics are piezoelectric, but
so
not vice versa.
So now here some of the properties are shown. For example, quartz, which is a piezoelectric material. It's a single crystal whose piezoelectric
Quartz.
coefficient is given as
Quartz.
2.33, and its stability permittivity is 4.5. Similarly, another material which is called the PVDF, it's a polymer material. It has certain piezoelectric property, and the piezoelectric coefficient is given as 21, and the stability permittivity is 12. Another material like barium titanate, it's a ceramic material. Piezoelectric constant is given as 78, and it has a very high permittivity which is equivalent to 1700. And now this barium titanate, it has different axes, and according to these axes, this permittivity can be changed from 1700 to 4000. Okay. So next is the PZT, which is called the lead zirconate titanate. It's another ceramic material whose piezoelectric constant is given as 110, and the permittivity is given as 1200. So it's very useful material uh, for microsensor that also has some piezoelectric property. Okay, with these values. Zinc oxide, it's another material which is a metal oxide, and with a permittivity of 1400, and it will show the piezoelectric coefficient or constant is as 246. And now if you see here this bottom table, that means stress sensitivity of different materials. So what is the effect on resistance if we apply certain mechanical pressure on particular body? Okay, if what is the effect on piezo resistive effect, what is the effect, how inductance changed, and the capacity, the piezoelectric is calculated. So here if you compare the values, there we have seen that those materials where stress sensitivity in case of piezoelectric material is highest, its value is given as 5 when comparison to other materials, which is 0.005. The piezo capacitance effect, the inductive effect is 0.001, and the piezo resistance is 0.0001, and only the resistance which is given as 0.000005. So that means compared to other property change, we found that the piezoelectric material, uh, the source, the piezo sensitivity is almost 5, which is a very large value, and this property may be fruitfully utilized. You can utilize it for making some piezo sensors or some other type of actuators. Okay, also. So now what are the advantages of the piezoelectric sensors? So there are meaningful advantages, and those advantages are namely, as it is extremely high rigidity materials and rigid material, high natural frequency is here. You can up to 500 kilohertz you can get with the piezoelectric materials. If you make sensor, it has the high reproducibility. It is extremely wide measuring range. So that means full scale is a very wide. You can get it extremely wide measuring range, very high stability, wide temperature range is also there. And so that is very important property which you cannot get in case of piezo resistance sensor. Okay, that's why piezoelectric sensor is much more useful compared to the piezoresistance sensor, because piezoelectric effect does not depend on the temperature. Okay, that is why this kind of sensors you can use in wide temperature ranges. Okay, and insensitivity to electric and magnetic fields and to radiation, that is also very important property. And whenever you use any sensors, lots of other electromagnetic fields are there. For example, a lot of cosmic radiation, like other ionic radiation. If you use that particular sensor in space, there will be, you can get rid of that. Not only that, electromagnetic field should be there, electric and different magnetic field also present. Even if you in a laboratory, there are certain amount of magnetic field or electric field may be available due to some line voltage or due to some high voltage equipment, or due to presence of very heavy magnet in the laboratory. You cannot get rid of that. So you want your sensor should not be disturbed with those radiation, the extra radiation or extra field. So in that respect, the piezoelectric material is one good choice, because this property or this effect does not depend on the radiation. It does not change with respect to the magnetic and any external electric field. Okay. Now, another property would like to discuss, that is the thermoresistivity. Thermoresistivity. So it is known, the different material will have temperature coefficient of resistance, that is thermoresistivity. And that means if you change the temperature, the resistance will change. That so that property is known as thermoresistivity. Now, the resistance changes with change in the temperature, and the well-known relation is here given as R equals to rho L by A, where rho is resistivity. You can write it as rho L by WT if A equals to WT, and then 1 by rho, which is the sigma, equivalent to sigma, equal to Q, mu n in plus mu p p. I think this equation I have discussed few classes ago. Okay, RT, which is here. So here, what I meant. So here RT, which is equal to the R naught into 1 plus alpha R into T minus T naught, where the alpha R is the temperature coefficient of resistance. Now this alpha R value is different for different material, and because of that alpha R change, you will get different thermoresistive property of different material. For example, you have different materials like carbon, magnesium, nichrome, chromium, aluminium, silver, copper, platinum, tungsten, iron, nickel, and gold, etc. Are present. So now these materials are frequently used in many microsensors, in MEMS, or in case of any VLSI design also. Okay, like the gold, which has the highest temperature coefficient, but this particular material you cannot use because of certain reason. And one of the reason I already mentioned earlier, that gold alone you cannot make the film with good adhesion. And although it is a noble metal, but the problem is the thin film does not adhere properly with gold. Then you have to take help from some other the adherence, other thin film material for proper adhesion with the substance. Okay, so gold is very rarely used for temperature coefficient sensitive sensor, or where the thermo resistivity effect is used. Okay, so rather one material another is nickel. Okay, so nickel, which is having very high alpha R for many cases. For example, the flow sensor, where the thermoelectric, uh, so this alpha R or temperature coefficient of resistance is this property is utilized. So there we use nickel as a sensing material. Okay, because of very high temperature coefficient of resistance value, and with that nickel as a sensing material, the only contact you can use for chromium gold. It does not matter, but nickel is a good choice for sensor when where you want to utilize the property of thermoresistivity. Okay, so next is the pyroelectricity. Pyroelectricity uh, the effect is basically development of electric polarization due to temperature change. Temperature change, that means if you change the temperature of that particular body or crystal or material, the electric polarization dipole realignment will be done inside that crystal. What happened, as a result of which you will have some certain charge at the surface, which is a pyroelectricity effect. Okay. So thermoelectric is a temperature change. Your resistance is changing. That is the thermoelectricity, which is earlier I have already mentioned. Now another is the pyroelectricity. That is again we are changing the resistance, but here we are getting some electric field charge you get at the surface. So both are dependent on the temperature. So the pyroelectricity effect is utilized in many cases of the temperature or radiation sensor. Okay, iron radiation sensor or many other high temperature measurements. Sometimes pyroelectric materials are used, and it occurs in generally non-centrosymmetric crystals. Okay, so non-centrosymmetric crystal means actually like crystal symmetry. First you have to understand that crystal symmetry. Okay, so in well formed crystals, what I mean, the symmetrically arranged faces, it reflects the internal arrangement of the atoms. Okay, the symmetry of individual crystals is determined by reference uh, to three elements, more like the plane of symmetry, which is called the mirror plane. That is the plane by which the crystal may be divided into two halves, which are mirror image of each other. That is the crystal symmetry. Okay, now a structure with a center of symmetry is called centrosymmetry. Now when the structure is with no center of symmetry is called non-centrosymmetric. Okay, so it occurs in the non-centrosymmetric crystals. That's all. So basically it is observed in case of non-centro uh, symmetric crystals. Again, all pyroelectric materials are also piezoelectric, not vice versa, because pyroelectric is a subset of the piezoelectric material. So pyroelectricity, you can, all pyroelectric materials basically shows the shows the uh, piezoelectric effect. Okay, so that means all piezoelectric may not show the pyroelectric, but all the pyroelectric will show the piezoelectric effect. Okay, now this P sigma, that is equal to the relation of del P by del T. Okay, where P stands for polarization and T is the temperature change. So materials in the pyroelectricity, with materials which shows the pyroelectric effect, are zinc oxide, lead zirconate titanate, and lead titanate, PbTiO3. Okay, so here you see among three materials, these two materials PZT and the lead titan is having some lead composition, but zinc oxide does not have. So lead material normally is not used in case of the VLSI process line, because lead and a single material, it is not an user friendly material. Okay, it is some kind of hazard chemical. So that is why now it is zinc oxide material is used frequently for either piezoelectric material or pyroelectric material rather than PZT or lead titanate. Okay. Now, earlier PZT and lead titanate were used for making sensor where the MEMS technology is not used and where the peripheral integrated circuit is not connected. So then individually you can process it. You may not bring those material into clean room environment, so there is no problem. But if you go for MEMS technique or MEMS based devices methods for making those sensors, then obviously you have to choose certain material which is user friendly to the VLSI process, and because you should not contaminate the whole process, the whole thing with the process equipment or the process gadgets, means the accessories, by lead contamination. Okay, so that is why out of the three materials, zinc oxide is much popular, and a lot of work is going on based on this zinc oxide nowadays. So next, another property is called the black body radiation. All objects with a temperature above the absolute zero, it emits the energy in the form of electromagnetic radiation. Okay, now a black body is a theoretical or a model body which absorbs all radiation falling on it, reflecting or transmitting none. Okay, so it is a hypothetical object which is a perfect absorber and a perfect emitter of radiation over all wavelengths. Okay, so black body is a radiation. The equation is given by this Planck's equation. And what is the Planck's equation? Planck's equation is the relation between the radiant flux and the emissivity at a particular temperature. So radiant flux is basically the spectrum flux density denoted by W lambda, and emitted by black body emissivity of the epsilon at temperature temperature T, and the whole thing is given by this equation, which is given here, W lambda equal to epsilon lambda 2 pi hc square W per centimeter square. So where epsilon is the degree to which it is basically to find as a degree to which a body emits less efficiently than a black body, and for black body it is considered as 1. This epsilon value should be 1. Okay, and another important equation which is used in case of radiation physics, that is the Wien's displacement law, which is the lambda peak equal to 2898 divided by T micrometer. Okay, where 2898, that is the Wien's displacement constant, and T is the temperature in absolute in micrometer. Okay, that means all body which is heated, it emits certain radiation, and wavelength of that radiation is given by this relation. Okay, and another equation is very important, which is Stephen Boltzmann's equation, and it is and that also if you hit a body of the temperature T, it emits certain radiation, and that radiation flux emitted from the body, that is the WT, which is given by the epsilon sigma T to the power 4, where T is the temperature and the epsilon and the sigma, so sigma is the Stephen Boltzmann constant, epsilon is the permittivity. Okay, so these are the relations used in case of black body radiation, so that it's a normal, the power available from a particular body is calculated in this technique, and the radiation flux at different wavelength are there, because different body or different temperature emits different wavelengths, which is given by this equation, which is the Wien's displacement given by the Wind displacement law. Now suppose there is a radiation pyrometer, one sensor or a device which is used for measuring very high temperature, because uh, we use thermocouple in case of a low temperature purpose. But if you want to measure the temperature in the range of 1500 2000 degrees centigrade, for example, if you want to measure the temperature of a blast furnace, okay, what happened, the temperature is in the range of 800 more than 1000. So the temperature is very difficult to measure using the conventional thermoelectric effect. So that sensor, if you use thermocouple sensor, you cannot get it, because at that temperature the material will soft melt if you use thermocouple. But there one technique, you can use the radiation parameter. So radiation parameter basically uses these laws, Stephen's law and Wind's displacement law. So the radiation in that body, if you absorb it wavelength, it emits, and that from the wavelength you can calculate the temperature. So that is one of the applications of the radiation sensors. So now comes to the optical properties. So there is a class of MEMS which is known as MOEMS, MOEMS, micro optoelectrical or optomechanical system, that is MOEMS. So these MEMS use the optical properties of the material. So we have to know a little bit about the optical properties also. So this particular figure shows the electromagnetic spectrum, basically the visible spectrum. We can see the radiation from red to violet, and red is 0.77 micrometer. So in between you will get blue, green, yellow, orange. These are visible range, and other than the visible range, the ultraviolet here, ultraviolet and infrared charge frequency used in many sensors. And ultraviolet range is from 0.39 from this position to 0.01 micrometer. Okay. On the other hand, infrared, now near infrared, medium infrared, or far infrared, okay, they are separated different spectrum region, and it exists from this position, from 0.77 to 0.77 micrometer to 1000 micrometer, which is extreme infrared region. Now, so in between this infrared and ultraviolet, there are certain wavelength ranges or frequency spectrum. Frequency ranges in the left side of the wavelength is in the right side. So for example, radio waves, long electrical oscillation, infrared or ultraviolet, X-ray, gamma ray, cosmic rays in this range. So this is the complete spectrum is given by this particular diagram. Okay. So different sensor operates in different spectrum according to the spectral location and according to the property of the sensor, that will also change. Now there are two kind of optical effect in case of material which is used in case of sensor. One is the photovoltaic effect, other is the photoelectric effect. Now both effects basically based on the photon. Photon is incident on that particular body. You will get photovoltaic or photoelectric. What is the difference between these two is mentioned here. On absorption of the photons, that means optical energy, when there is a transition from valence to conduction band, that effect is known as photovoltaic effect. On the other hand, on the absorption of the photo energy, if the transition of the carrier is from conduction band to the vacuum, so it is known as the photoelectric effect. Okay, so both effects are used in making sensor. So obviously, if we use semiconductor material, then the energy of the photon will be such that the electron can have a transition from valence band to the conduction band. Okay, that means the photon energy is given by here h nu So H nu must be greater than the band gap, which is represented by Eg in some band gap diagram I have explained earlier. Okay, so if that energy is less than the band gap energy, so that will not, so any of this optical effect or it will not change the properties, then it emits to the crystals, and those things are known as the optical windows basically. So there is no transition, but if H nu is greater than the band gap energy, so there will be a transition. There is a possibility some of the carriers will jump from valence band to the conduction band of the carrier, so it may go from conduction band to the vacuum level, as a result of which we will, if the movements of the carriers are there, you will get some current, and that is known as the photocurrent. Now its energy, which is here E equals to the H nu and is given by Hc by lambda, and for far infrared that this is a 10 to the power 11 hertz to that is the new frequency, and for ultraviolet that is for 10 to the power 17 hertz. So there is a law which is known as the Beer's law, okay, which it relates to the observation of the radiation of different material. So the observation is a function of depth. So if photon is incident on a body, so this photon is absorbed. First it has to be absorbed, then other effects will show one by one. So this absorption is again is a function of the depth. So some of the radiation is depends on the energy, so it goes higher depth and it is observed there, and some of the radiation cannot penetrate its higher depth, and the Beer's law states that the absorption equals to A is equal to the A naught e to the power minus alpha x into x, where this alpha is known as the absorption coefficient and x is the depth, and A naught is obviously x is equal to 0, so A is equal to so A naught. So at this surface the absorption is A0, and then you go higher and higher depth, and obviously the A value will reduce, and that is the Beer's law, it will reduce. Okay, so now the optical properties in the semiconductor I would like to discuss. So if you consider it on the direct band semiconductor, which is gallium arsenide, or so, so that means here here minimum of the conduction band and the maximum of the valence band on the same wave number, it is aligned on the same wave number. So in a movement of axis, so that the transition from the valence band to conduction band, which is direct, there is no loss of energy in between. Okay, so from valence band to conduction band there is no loss of energy. So that is basically the direct band semiconductor with no phonon is necessary for electron transfer. What is phonon? Phonon is basically the lattice vibration, that energy, this kind of energy is called the phonon, and photon is the optical radiation energy. Okay, now no phonon necessary directly from valence to the conduction band to it transfer, and as a result of which you can have some radiation from there whose color depends on the band gap energy value, which is calculated from Eg, which is equal to the nu H nu from that relation, the previous relation. Now on other hand, indirect band of semiconductor examples are silicon and germanium. So there you see direct transmission, direct transition is if there is it is not possible. So now here's the minimum of the conduction band and the maximum of the valence band do not lie on the same wave number. So in the different wave number it is happened, so as a result of which there will not be a direct transition. So first, from the valence band top, it will go here in this position. Then it transfer in the conduction band. So here probability of going the carrier from valence band to the conduction band is less because the semiconductors are indirect band gap. So it will goes through some lattice collision. So here the phonon is required. So probability of using optical device, it is decreases, and it is two particle processes, because from here you require another particle. Okay, so so thereafter the collision, or say scattering, from here it goes to the optical devices, whether this the direct band semiconductor are much popular in case of optical devices. Okay, optical MEMS based sensor devices. So with this, just I finished this particular topic, the material of properties. Basically it's based on the material of properties. Okay, so that's all for today. If you have any doubts and inquiries, you can ask. Unmute yourself and you can ask the question. Do you have any queries?
No, sir.
Okay, Nila bro.
Sir. Yes, sir.
So all the lecture videos are uploaded in the YouTube, and the links has been uploaded in the Google Classroom. Okay, you can
Okay, sir.
check the videos from the previous topics. Okay, and if you have any queries, you can ask me later.
Okay, sir. I will check. Okay, sir.
সুপ্রতীক। Okay, if you don't have any queries, you may leave now. And what about the Alam? You have asked me some question regarding some project experience.
Yes, sir. Yes, sir. Yes, sir.
Tell me now.
I saw projects where a sandal was designed for a girl or woman. It will get charged while they are walking, and if some unfortunate thing happens, then she can just slap the guy from his or her sandal, and it will generate a shock.
That means shock sensor.
Is it possible? Yeah,
But
not shock
vibration.
sensor. Say,
Yes, it will
yeah,
vibrate certain level.
it gets charged from the vibration from the pressure. Okay, and the battery gets charged from the movement of just like walking. Okay,
So in that case,
and
you have to use the piezoelectric material, obviously.
yes, sir, they have used piezoelectric materials, but they have used six piece of piezoelectric material. So I was thinking, is that enough to charge a battery? Strong enough to power an electric shock?
It based on the calculation, because you need to calculate certain level of voltage. Okay, how much voltage
So
will be
it generates
generated.
millivolts. So
So it's very
a battery
less. It's
requires
very less.
definite kind of voltage. So I don't think it's actually that's why I was asking you, and they got a prize also.
How can they make these things? Can you
Actually,
explain?
I was also working on that, sir, but the design wasn't good, and